Hello, and welcome to the Sleepyhead Geographer. Tonight, we're going to witness something truly extraordinary. We're going to watch as volcanoes, hidden deep beneath miles of ocean water, slowly and patiently give birth to brand new land. It's a story that unfolds over thousands, sometimes millions of years, yet each moment is filled with the raw creative power of our living planet. Let's imagine ourselves as patient observers, able to watch time pass like pages turning in a cosmic book. We'll see how fire and water work together in the most unexpected ways, how destruction becomes creation, and how the earth itself builds new homes for life to flourish. This is not a violent story, despite the power involved. It's gentle, methodical, and profoundly peaceful in its ancient rhythm. Picture yourself drifting through the warm waters of the Pacific Ocean, perhaps somewhere between California and Japan. The surface above us sparkles with sunlight. But we're descending now, down through layers of increasingly blue water. As we go deeper, the light begins to fade, shifting from bright azure to deeper navy, then to a mysterious twilight blue that seems to hold secrets in every shadow. We pass schools of fish swimming in perfect formation, their silver sides catching what little light penetrates this deep. Jellyfish drift by like living parachutes, translucent and graceful in their eternal dance through the water column. But we're going deeper still, down past the familiar world of sea life, down to where the ocean floor spreads out like a vast underwater plain. Here, 3 miles beneath the surface, we find ourselves in a world of perpetual twilight. The water pressure is enormous, hundreds of times greater than at the surface. Yet the ocean floor is not the barren wasteland we might imagine. It's a landscape of gentle hills and valleys, of underwater mountains and vast abyssal plains that stretch for thousands of miles. And it's here, in this seemingly quiet and unchanging world, that our story begins. For deep beneath the ocean floor, something magnificent is stirring. The Earth's mantle, that layer of hot, semi-molten rock that lies beneath the thin crust we call the seafloor, is in constant, slow motion. Like thick honey being gently stirred, currents of hot rock rise and fall in patterns that have continued for billions of years. In certain special places we call hotspots, these currents of hot rock create something like underwater chimneys. Imagine a column of exceptionally hot material rising through the mantle, carrying with it the potential for creation. These hotspots remain relatively stationary, while the ocean floor above them moves slowly across their surface, like a conveyor belt passing over a candle flame. Tonight, we'll follow the journey of one such hotspot as it begins the slow, patient work of building an island. We'll watch as molten rock first finds its way through cracks in the ocean floor as it builds underwater mountains that grow taller with each eruption, and finally as it breaks through the surface of the ocean to create new land where none existed before. But this is more than just a geological story. It's a story of patience and persistence, of how the Earth creates homes for countless forms of life. We'll see how bare rock becomes a living ecosystem, how plants and animals find their way to these remote new lands, and how each island becomes a unique world unto itself. The process we're about to witness has created some of the most beautiful places on Earth. The Hawaiian Islands, the Galapagos, Iceland, and countless other island chains all began exactly as we're about to see, as tiny cracks in the ocean floor through which the Earth's inner fire found its way to the surface. As we begin this journey together, let's remember that we're witnessing one of the most fundamental processes of our planet. This is how the Earth renews itself, how it creates new land, new opportunities for life, and new wonders for future generations to discover. It's a reminder that our planet is not a static, unchanging world, but a living, breathing, creating entity that continues to shape itself even as we sleep. So let's take a deep breath of that clean ocean air, feel the gentle motion of the waves, and prepare to witness one of nature's most magnificent and patient acts of creation, the birth of an island. Our story begins in absolute darkness, 3 miles beneath the Pacific Ocean's surface, where the water pressure could crush a submarine and the temperature hovers just above freezing. Here, on the abyssal plain, the seafloor stretches endlessly in all directions like an underwater desert. But unlike the deserts we know on land, this one is carpeted with the finest sediment, the accumulated remains of countless microscopic sea creatures that have drifted down like snow for millions of years. The silence here is profound, broken only by the occasional distant call of a whale far above, transmitted through the water like a ghost song from another world. Yet beneath this seemingly peaceful seafloor, something extraordinary is stirring. Deep in the Earth's mantle, perhaps 50 miles below where we float, a column of superheated rock has been rising slowly, inexorably, for thousands of years. This rising plume of molten material, heated to temperatures exceeding 2,000 degrees Fahrenheit, represents one of the Earth's most primal forces. It carries within it the power to create continents, to reshape ocean basins, and tonight, to give birth to an island. As this plume approaches the underside of the oceanic crust, the relatively thin layer of volcanic rock that forms the ocean floor, it begins to melt everything it touches. The oceanic crust here is young by geological standards, perhaps only 50 million years old, formed at a distant mid-ocean ridge and carried here by the slow but relentless motion of tectonic plates. It's composed primarily of basalt, a dark, dense volcanic rock that formed when underwater eruptions cooled rapidly in contact with seawater. But now, this solid rock foundation is about to become something far more dynamic. As the rising mantle plume encounters the crust from below, it begins to create what geologists call a melt zone. The intense heat doesn't just soften the rock, it fundamentally changes its structure, transforming solid basalt back into the liquid magma from which it originally formed. This process happens gradually, over hundreds of years, as the plume slowly works its way through the overlying rock layers. The first sign of what's to come appears as a subtle warming of the seafloor. In this realm where temperatures normally remain constant year after year, even a few degrees of change represents a dramatic shift. Deep-sea creatures that have adapted to the stable cold begin to sense something different. The giant tube worms that cluster around hydrothermal vents miles away seem to know instinctively that change is coming to their ancient world. Then, perhaps on a Tuesday morning, though of course time has no meaning in this sunless realm, the first crack appears in the seafloor. It's tiny at first, no wider than a pencil, running for perhaps 20 feet across the sediment-covered basalt. But through this hairline fracture, something remarkable begins to emerge. The Earth's first breath of what will become an island. The crack doesn't dramatically split open like something from a disaster movie. Instead, it widens slowly, almost gently, as the pressure from below gradually overcomes the structural integrity of the rock above. As it widens, the first molten rock begins to seep through, not in a violent explosion, but in a slow, steady flow that's more like thick honey than liquid fire. This first submarine eruption is unlike anything we might see on land. Here, 3 miles underwater, the enormous pressure changes everything about how volcanic activity behaves. When the 2,000-degree molten rock meets the near-freezing seawater, it doesn't create the spectacular lava fountains we associate with volcanoes. Instead, it forms what geologists call pillow lava, bulbous, rounded shapes that look remarkably like giant stone cushions. The process is almost gentle in its deliberate pace. As molten rock emerges from the crack, the seawater instantly cools its outer surface, forming a flexible skin of solid rock. But the interior remains molten, and as more material pushes up from below, these rock pillows grow and bulge, eventually breaking open to create new pillows in an endless, patient cycle. If we could watch this process in time-lapse, speeding up thousands of years into minutes, we would see something like an underwater flower garden slowly blooming. Each pillow of lava adds to the growing mound, and gradually, what started as a tiny crack in the seafloor begins to build upward. The first small hill of volcanic rock takes shape, perhaps rising 10 feet above the surrounding seafloor. But our infant island-to-be faces its first challenge: the sea itself. The ocean at this depth is not the peaceful, warm water we know at the surface. It's a harsh environment where nothing stays unchanged for long. Strong, deep ocean currents, driven by temperature differences thousands of miles away, sweep across the seafloor with surprising force. These currents carry abrasive sediment that can wear away exposed rock, threatening to erode our tiny volcanic hill faster than it can grow. Yet the Earth is patient and persistent. Each new eruption adds more rock to the growing mound, and gradually, the volcanic hill begins to establish itself as a permanent feature of the seafloor landscape. As it grows taller, it begins to affect the local ocean currents, creating eddies and variations in flow that will eventually trap sediment and provide shelter for the first pioneering forms of life. The chemistry of the water around our growing seamount begins to change as well. The volcanic activity releases dissolved minerals and gases that have been locked away in the Earth's interior for millions of years. Iron, sulfur, magnesium, and dozens of other elements begin to create a unique environment around the base of the growing volcano. These chemical changes, invisible to the naked eye but profound in their implications, will eventually attract specialized forms of life adapted to thrive in such conditions. As our seamount continues to grow, now perhaps 50 feet tall and several hundred feet across at its base, it begins to develop a more complex structure. The original crack expands into a network of fissures, each one providing a pathway for molten rock to reach the surface. The eruptions become more frequent, though still following the same gentle, pressure-controlled pattern that creates the characteristic pillow lavas. The growing volcano also begins to develop what will eventually become rift zones, linear areas of weakness that extend outward from the central eruption point like the spokes of a wheel. These rift zones are crucial to the island-building process, as they allow volcanic activity to spread outward, creating a broad, stable foundation rather than just a tall, narrow spire that might be vulnerable to collapse. Marine life begins to take notice of this new addition to their neighborhood. Deep-sea fish, adapted to the unchanging conditions of the abyssal plain, are initially wary of the warm water and chemical changes around the seamount. But gradually, some species begin to explore this new habitat. Small fish discover that the complex rocky surfaces provide shelter from predators, while filter feeders find that the mineral-rich water carries nutrients they can't find elsewhere on the barren seafloor. By now, our seamount has been growing for perhaps 10,000 years, reaching a height of several hundred feet above the surrounding seafloor. It's still nowhere near the ocean surface. It has nearly 3 miles yet to climb, but it has established itself as a major geological feature. Its base now spans several miles, and its presence has begun to influence ocean currents across a much wider area. The volcano's internal structure is becoming more sophisticated as well. Deep beneath the pillow lavas that form its exterior, a complex network of magma chambers and conduits is developing. These underground spaces serve as staging areas where molten rock can accumulate and evolve chemically before being erupted. This development is crucial because it will eventually allow for larger, more sustained eruptions that can build the seamount more rapidly. As we watch our underwater mountain continue its patient growth, we're witnessing the very earliest stage of a process that will take hundreds of thousands of years to complete. But already, the fundamental character of our future island is being established. Its foundation is being built grain by grain, pillow by pillow, eruption by eruption, in the patient darkness of the deep ocean floor. As tens of thousands of years pass in our underwater realm, our volcanic seamount has transformed from a small crack in the sea floor into a substantial underwater mountain. Rising now nearly 1,000 feet above the abyssal plain, it has become a landmark in this deep sea world, visible to the occasional deep-diving whale or military submarine that passes overhead like a shadow against the faint glow filtering down from the surface far above. The character of the eruptions has begun to evolve as well. What started as gentle seepages of pillow lava has developed into more organized volcanic events. The internal plumbing system of our growing mountain has become increasingly sophisticated, with multiple magma chambers at different depths working together like the chambers of a vast underground heart, pumping molten rock toward the surface in rhythmic pulses. Deep beneath the seafloor, perhaps 10 miles down, the primary magma chamber has grown to enormous proportions. This underground cavern, filled with molten rock at temperatures exceeding 2,100 degrees Fahrenheit, serves as the staging area for all the volcanic activity above. Here, in this fiery cathedral beneath the sea, different types of molten rock mix and evolve, their chemical compositions changing as they interact with each other and with the surrounding solid rock. The pressure at these depths is almost incomprehensible, thousands of times greater than at the Earth's surface. Under such conditions, molten rock behaves very differently than we might expect. It becomes less viscous, more fluid, allowing it to carry dissolved gases and minerals that would escape under lower pressure conditions. This high-pressure environment is crucial to the island-building process, as it allows the magma to transport the raw materials needed to construct an entire mountain. As our seamount continues to grow, it begins to develop distinct zones of volcanic activity. The central area, directly above the main magma chamber, experiences the most frequent and vigorous eruptions. Here, pillow lavas pile upon pillow lavas in endless profusion, building a steep-sided central cone that will eventually become the heart of our island. But equally important are the rift zones, linear areas extending outward from the central cone where secondary fissures allow molten rock to reach the seafloor. These rift zones are architectural marvels in their own right. They extend for miles outward from the central volcano, creating long ridges of volcanic rock that serve as the foundation for what will eventually become the broad, shield-like shape characteristic of oceanic islands. The eruptions along these rift zones are typically gentler than those at the central vent, producing steady flows of pillow lava that spread outward like the roots of a great stone tree. The process of building these underwater foundations requires an almost unimaginable amount of molten rock. Each cubic mile of seamount represents hundreds of individual eruptions, each one depositing its load of pillow lavas onto the growing structure. The total volume of rock needed to build a seamount tall enough to eventually reach the ocean surface is staggering, often exceeding the volume of rock that makes up entire mountain ranges on land. As our seamount grows taller, the environment around it begins to change in fundamental ways. The deep ocean currents that once flowed smoothly across the flat seafloor now encounter this massive obstacle, creating complex patterns of upwelling and downwelling that affect water chemistry and temperature across hundreds of square miles. These current patterns help to trap sediment around the base of the seamount, gradually building up thick deposits of marine snow, the constant rain of organic particles that falls from the upper layers of the ocean. The chemical environment around our growing volcano becomes increasingly complex as well. Each eruption releases not only molten rock, but also dissolved gases and minerals that have been stored deep within the earth. Hydrogen sulfide, carbon dioxide, sulfur compounds, and trace metals create a unique chemical signature in the water surrounding the seamount. While these concentrations are far too low to be dangerous, they're sufficient to attract specialized forms of marine life that have evolved to take advantage of such mineral-rich environments. The first complex ecosystems begin to establish themselves around our seamount when it reaches a height of about 1,500 feet above the sea floor. Deep-sea corals, unlike their shallow water cousins, don't require sunlight to survive. Instead, they filter nutrients directly from the water column, and they find the mineral-rich water around active volcanic areas particularly hospitable. These cold-water corals begin to colonize the rocky surfaces of the seamount, creating the first three-dimensional habitat structures in what was once a barren underwater desert. The coral colonies, in turn, attract other forms of life. Small crustaceans find shelter among the coral branches, while various species of deep-sea fish discover that the complex topography of the seamount provides both hunting grounds and hiding places. Tube worms, adapted to the chemical-rich environment around underwater volcanic areas, establish colonies near active vents, creating bizarre garden-like formations that wave gently in the deep-sea currents. But perhaps the most remarkable aspect of this underwater construction project is its sheer persistence. Volcanic activity on our seamount doesn't follow human timescales. It operates on geological time, where patience is measured in millennia rather than minutes. There may be decades or even centuries between major eruptions, periods during which the surface of the seamount becomes colonized by marine life and covered with sediment. But inevitably, the volcanic fires below reignite, breaking through these temporary surfaces and adding new layers to the growing structure. As our seamount passes the halfway point in its journey to the surface, now reaching heights of nearly a mile above the sea floor, its internal architecture becomes increasingly sophisticated. Multiple magma chambers at different depths create a complex network of molten rock reservoirs, each one evolving chemically in its own unique environment. The deepest chambers, closest to the original mantle plume, contain the most primitive basaltic magmas, while shallower chambers allow for more chemical evolution and differentiation. This chemical evolution is crucial to the eventual character of our island. As magma sits in shallow chambers, it begins to change composition through a process called fractional crystallization. Certain minerals crystallize out of the melt and settle to the bottom of the chamber, while others remain dissolved in the liquid portion. This process gradually changes the chemical makeup of the magma, making it less dense and more gas-rich, characteristics that will become important when the volcano eventually reaches the ocean surface. The growing seamount also begins to affect the regional geology of the ocean floor. Its immense weight, now measuring in the billions of tons, begins to depress the sea floor around its base, creating what geologists call a moat, or flexural depression. This depression, typically extending for dozens of miles around the base of large seamounts, affects the local topography and water circulation patterns across a vast area. As we watch our seamount continue its patient climb toward the distant surface, we can begin to see hints of the island it will eventually become. The broad, shield-like shape is already apparent, with the central volcanic cone rising steeply from a wide base built by countless eruptions along the rift zones. The internal structure, the complex network of magma chambers, conduits, and storage areas, represents the foundation upon which all future volcanic activity will be built. Marine life around the seamount has also begun to develop characteristics that will persist even after the volcano reaches the surface. The unique chemical environment created by volcanic activity has attracted specialized species from across the ocean basin, and some of these early colonists will eventually play important roles in the terrestrial ecosystems that will develop once the island emerges. By now, our seamount has been growing for perhaps 50,000 years, and it stands nearly 1.5 miles tall above the original seafloor. It dominates the local underwater landscape, visible to deep-sea creatures from many miles away. Its presence has fundamentally altered the physical, chemical, and biological environment of this part of the ocean. But the most remarkable phase of our island's birth still lies ahead. Our seamount still has more than a mile of water above it before it will taste its first breath of surface air. The final push to the surface will bring new challenges and new opportunities, as the nature of volcanic activity changes dramatically when it encounters the very different environment of the shallow seas. The day our seamount first tastes sunlight is a day like no other in its 100,000-year history. After patient millennia of growth in the eternal darkness of the deep ocean, the summit of our underwater mountain has finally climbed to within a few hundred feet of the surface. Here, in the photic zone where sunlight can still penetrate the water, everything changes. The water at this depth is a brilliant turquoise, alive with microscopic organisms that form the foundation of oceanic food webs. Shafts of sunlight dance through the water column, creating an ever-shifting pattern of light and shadow that our mountain has never before experienced. Schools of fish that have never ventured into the deep waters below now swim curiously around the volcanic slopes, their scales flashing silver in the filtered sunlight. But it's not just the presence of light that makes this zone different, it's the dynamic nature of the shallow ocean environment. Here, waves and currents have far more energy than in the deep sea. Storm waves, generated by weather systems hundreds or thousands of miles away, reach down into the water column with surprising force. These waves begin to interact with our seamount's summit, creating the first hints of the turbulent relationship between fire and water that will define our island's emergence. The volcanic activity itself begins to change character as the summit approaches the surface. The enormous water pressure that has governed eruptions for so long gradually decreases, allowing dissolved gases in the magma to expand. This expansion changes the very nature of the eruptions, making them more explosive and dynamic than the gentle pillow lava formations that built the seamount's foundation. When the summit finally reaches a depth of about 300 feet below the surface, the first dramatic change occurs. During a particularly vigorous eruption, the expanding gases in the magma create something that hasn't happened in our volcano's entire history: a true explosive event. The eruption sends a column of superheated water, steam, and volcanic fragments rocketing toward the surface, breaking the ocean's calm in a spectacular display that can be seen from space. This first explosive eruption marks the beginning of what volcanologists call the emergent phase of island formation. It's a period of intense activity as our volcano struggles against the ocean itself, each eruption battling not only the pressure of the overlying water, but also the erosive power of waves and currents that work constantly to tear down what the volcano builds up. The early submarine explosive eruptions create a unique type of volcanic material called hyaloclastite, fragments of volcanic glass formed when molten lava comes into violent contact with seawater. These glass fragments accumulate around the summit of the seamount, creating loose, unconsolidated deposits that are easily eroded by wave action. For a time, it seems as though our volcano might never succeed in building a permanent structure above sea level. But the Earth's patience exceeds even that of the ocean. Each eruption deposits more material, and gradually, the summit cone becomes more substantial. The explosive eruptions also begin to create a different type of internal architecture. vertical conduits that allow magma to travel rapidly from deep chambers to the surface. These conduits, formed by the explosive clearing of previous eruption debris, will become crucial to the island's eventual success in breaking the surface. As the summit approaches to within 100 feet of the surface, marine life in the area begins to experience dramatic changes. The explosive eruptions create clouds of superheated water that rise rapidly to the surface, carrying with them dissolved minerals and gases from deep within the earth. While these chemical changes are temporary, they create temporary dead zones around the eruption site as marine organisms flee the altered conditions. But life, like the volcanic process itself, is remarkably adaptable. Between eruptions, when conditions return to normal, marine life quickly recolonizes the area around the seamount. Some species even seem to benefit from the mineral-rich water created by volcanic activity, growing more rapidly and reproducing more successfully than their counterparts in unaffected areas. The final approach to the surface is marked by increasingly frequent and violent eruptions. The summit cone, now only 50 feet below the surface, experiences eruptions almost daily. Each one sends a column of superheated water and steam rocketing to the surface, creating temporary islands of floating volcanic debris that last only minutes or hours before being dispersed by waves and currents. Then, on a day that dawns like any other, the moment finally arrives. During a particularly sustained eruption, enough volcanic material accumulates at the surface to remain there permanently. The first tiny speck of our island, perhaps no larger than a small house, breaks through the waves and tastes air for the first time in its existence. This emergence is not the dramatic, permanent breakthrough we might expect. The first appearance of land is tentative, vulnerable. The newborn island is little more than a pile of loose volcanic debris, constantly battered by waves and in danger of being washed away before it can establish itself. Many potential islands fail at this crucial stage, their emergence lasting only days or weeks before the ocean reclaims them. But our island has something working in its favor: the continued vigorous eruption that brought it to the surface in the first place. As waves wash away loose debris from the edges of the tiny landmass, the ongoing volcanic activity continues to add new material to its center. It's a race between construction and destruction, with the fate of our newborn island hanging in the balance. The character of the eruptions changes dramatically once volcanic activity encounters air rather than water. The expanding gases that were constrained by water pressure now escape more freely, creating spectacular fountains of molten lava that can be seen for miles across the ocean. These lava fountains, while dramatic, also serve a crucial purpose. They create more substantial, coherent rock structures that are better able to resist wave erosion. The first volcanic rocks to solidify in contact with air are different from anything formed during the seamount's underwater growth phase. These subaerial lavas cool more slowly than their underwater counterparts, allowing larger crystals to form and creating rocks that are denser and more resistant to weathering. Each successive eruption builds upon these solid foundations, gradually creating a more permanent and substantial landmass. The newborn island also begins to affect its local environment in ways that will help ensure its survival. The presence of land changes local wave patterns, creating areas of calmer water on the lee side of the island where loose volcanic debris can accumulate more easily. The landmass also begins to affect local weather patterns, creating updrafts that can influence cloud formation and precipitation. Within weeks of its first emergence, our tiny island, still no more than a few acres in extent, experiences its first rainstorm. The fresh water that falls on the volcanic rocks begins the very first stages of soil formation as it chemically reacts with the minerals in the lava. This early weathering process, while barely detectable, marks the beginning of the transformation from lifeless rock to potential habitat. The island's first few months of existence are precarious. Winter storms bring larger waves that threaten to wash away the loose debris that still makes up much of the landmass. But each storm is also followed by renewed volcanic activity, as if the Earth itself responds to the challenge by increasing its efforts to build the island higher and stronger. As our island celebrates its first anniversary of emergence, it has grown to perhaps an acre in size and risen to a height of about 50 feet above sea level. It's still a raw, hostile environment. A pile of volcanic rock constantly swept by salt spray and battered by waves. No life has yet found a foothold on its shores. But it has achieved something remarkable. It has established a permanent foothold in the battle between fire and water, creation and destruction. In the decades following its dramatic emergence from the sea, our newborn island enters what geologists call the shield-building phase, a period of steady, sustained volcanic activity that will determine its ultimate size and character. This phase represents the golden age of island construction, when continuous eruptions gradually transform a tiny pile of volcanic debris into a substantial landmass capable of supporting complex ecosystems. The volcanic activity during this shield-building phase is markedly different from the explosive eruptions that characterized the island's emergence. Now that the summit has risen well above sea level and established stable conduits to deep magma chambers, the eruptions become more effusive, characterized by steady flows of molten lava rather than violent explosions. These lava flows, with temperatures often exceeding 2,000 degrees Fahrenheit, pour from multiple vents across the island's surface like glowing rivers of liquid rock. The island's internal structure continues to evolve during this critical period. Deep beneath the growing landmass, a sophisticated network of magma chambers, conduits, and storage reservoirs reaches full maturity. The primary magma chamber, now located approximately 6 miles beneath the island's summit, serves as the central hub for all volcanic activity. From this main reservoir, secondary chambers branch outward, each one feeding different areas of the island's surface through an intricate plumbing system of underground channels. One of the most remarkable features to develop during the shield-building phase is the rift zone system, linear areas of volcanic activity that extend outward from the central summit like the spokes of a wheel. These rift zones become the primary sites for the steady lava flows that will build the island's broad, gently sloping sides. Unlike the steep-sided volcanic cones we often imagine, oceanic shield volcanoes are characterized by their massive size and relatively gentle slopes, rarely exceeding more than a few degrees of incline. The lava flows that characterize shield building create some of the most spectacular geological features on Earth. These flows can travel for miles from their source vents, following the natural contours of the land as they seek the path of least resistance toward the sea. As the molten rock encounters the ocean at the island's constantly expanding shoreline, it creates clouds of steam and forms new land through the dramatic process of quench cooling, the instant solidification that occurs when 2,000-degree lava meets near-freezing seawater. This interaction between lava and sea creates a type of coastline found nowhere else on Earth. The shoreline of an actively growing volcanic island is raw, primordial, a place where new land is being created literally before our eyes. Black sand beaches form where wave action breaks down fresh volcanic rock, while tide pools carved into new lava flows create temporary habitats that may exist for only months or years before being covered by subsequent eruptions. During its most active periods, our island grows at an almost incredible rate. Major eruptions can add several feet to the island's height, and hundreds of acres to its surface area in a matter of days or weeks. Over the course of several centuries, The island expands from its original acre or two to encompass dozens, then hundreds, then thousands of acres. Its height grows correspondingly, as lava flows stack upon lava flows, building the broad foundation that will eventually support mountains reaching thousands of feet into the sky. The chemical composition of the lavas also evolves during the shield-building phase. Early eruptions tend to produce relatively simple basaltic lavas, iron and magnesium-rich rocks that form the backbone of oceanic crust. But as the volcanic system matures and magma has more opportunity to evolve chemically in shallow chambers, the erupted lavas become more diverse. Different areas of the island may erupt lavas with subtly different compositions, creating variations in rock type that will eventually influence everything from soil formation to groundwater flow. The island's growing mass also begins to have significant effects on the surrounding ocean environment. The presence of substantial new landmass affects local current patterns, wave refraction, and even regional weather systems. As the island grows larger, it begins to create its own microclimate. The landmass causes air masses to rise and cool, leading to increased precipitation on the windward sides of the emerging mountains. This early climate modification has profound implications for the island's future development. The increased rainfall on certain parts of the island begins the crucial process of chemical weathering, the breakdown of volcanic rock into the minerals and nutrients that will eventually form soil. Even during the height of volcanic activity, when much of the island's surface is regularly covered by new lava flows, protected areas begin to accumulate the first thin layers of weathered material. The shield-building phase also sees the development of the island's first semi-permanent surface features. While individual lava flows may last only months or years before being covered by new eruptions, larger features like cinder cones, spatter ramparts, and lava tubes begin to establish themselves as lasting elements of the island's topography. These features, formed by specific types of volcanic activity, create the varied landscape that will characterize the mature island. Lava tubes, in particular, play a crucial role in the island's development. These natural tunnels, formed when the surface of a lava flow cools and solidifies while molten rock continues to flow beneath, allow lava to travel much farther from source vents than would otherwise be possible. Some lava tubes extend for dozens of miles underground, carrying molten rock from high on the island's slopes to the sea. These tubes not only help build the island more efficiently, but also create underground spaces that will later serve as aquifers and habitat for specialized forms of life. As our island continues to grow through its shield-building years, it begins to develop distinct geological zones that will influence its character for millions of years to come. The summit region, fed by the most direct conduits from deep magma chambers, tends to build the highest elevations and steepest slopes. The rift zones create broad ridges that extend toward the sea like massive stone buttresses, while the areas between rift zones develop gentler slopes built by smaller, more dispersed volcanic vents. The island's coastline during this period is in constant flux, expanding outward as new lava flows reach the sea and creating dramatically different types of shoreline depending on local conditions. Where lava flows enter calm, protected waters, they may build gradually outward, creating broad, gently sloping underwater platforms. But where flows encounter high-energy wave environments, the interaction between molten rock and turbulent seawater creates spectacular displays of steam and violence, building steep, unstable cliffs that may collapse periodically as wave erosion undermines their foundations. The scale of volcanic activity during peak shield building is almost incomprehensible by human standards. In a single year, major eruptions may produce enough lava to cover dozens of square miles with molten rock several feet deep. The total volume of material erupted during the most active centuries can exceed the volume of entire mountain ranges on continental land masses. This massive construction project transforms the seafloor topography across hundreds of square miles, as the growing island's weight continues to depress the underlying oceanic crust. One of the most remarkable aspects of shield building is the sheer variety of volcanic phenomena that can occur simultaneously across different parts of the island. While gentle lava flows characterize most of the activity, certain areas may experience more dramatic eruptions, spectacular lava fountains that shoot molten rock hundreds of feet into the air, creating curtains of fire visible from great distances across the ocean. These fountain eruptions often occur along active rift zones, where linear fissures allow molten rock to escape along extended fronts rather than through single-point sources. The island's internal temperature during peak shield building creates an environment unlike anywhere else on Earth's surface. Ground temperatures in active volcanic areas can exceed 150 degrees Fahrenheit, just inches below the surface, while active lava flows maintain temperatures hot enough to melt copper. The air itself shimmers with heat distortion, and the constant outgassing from cooling lava creates a unique atmospheric chemistry dominated by sulfur compounds, carbon dioxide, and water vapor. Yet even during this period of intense volcanic activity, the first signs of life begin to appear on the island. Hardy pioneer species, primarily microorganisms adapted to extreme temperatures and chemical conditions, establish footholds in areas where cooling lava flows create temporarily stable surfaces. These microbial communities, invisible to the naked eye but crucial to future ecosystem development, begin the slow process of biological succession that will eventually transform the island from a sterile volcanic wasteland into a living ecosystem. As the shield building phase reaches its peak intensity, our island has grown to encompass thousands of acres and rise to elevations of several thousand feet above sea level. Its broad, gently sloping profile, punctuated by the more dramatic relief of cinder cones and spatter ramparts, creates a landscape that is both alien and strangely familiar. The island's silhouette, visible from hundreds of miles away across the ocean, announces the presence of one of Earth's newest land masses. The climax of the shield building phase is marked not by increased activity, but by its gradual decline. As the deep mantle plume that feeds the island's volcanic system begins to weaken or shift position, the frequency and intensity of eruptions slowly decrease. This transition doesn't happen overnight. It may take centuries or even millennia for the change to become apparent. But gradually, periods between major eruptions become longer, and the volume of lava produced by each eruption begins to decrease. This transition marks a fundamental change in the island's development. Where once volcanic activity dominated every aspect of the island's growth, other processes, weathering, erosion, biological colonization, begin to play increasingly important roles. The island has reached the size and stability necessary to support complex ecosystems, and the stage is set for the next remarkable chapter in its development: the arrival of life. As our island celebrates its 10,000th year above the ocean's surface, it has achieved something remarkable: geological stability sufficient to support life. The frequent, overwhelming eruptions of the shield-building era have given way to longer periods of volcanic quiet, interrupted by occasional smaller eruptions that add to the island's bulk without completely destroying existing surface features. Into this world of cooling lava and stabilizing landscapes, life begins its most extraordinary journey: the colonization of a brand new world. The first life to establish itself on our island doesn't arrive in the way we might expect. There are no dramatic migrations or obvious moments of colonization. Instead, life arrives quietly, almost invisibly, carried on the wind and waves in forms so small they escape casual notice. Microscopic spores of bacteria, fungi, and primitive plants travel thousands of miles through the atmosphere, suspended in air currents that circle the globe. Some of these microscopic travelers, after journeys that may have lasted weeks or months, finally settle on the cooling volcanic surfaces of our island. The early microbial colonists faced challenges unlike those encountered anywhere else on Earth. The island's surfaces are composed entirely of fresh volcanic rock, completely devoid of the organic compounds and nutrients that life typically requires. Temperatures on dark lava surfaces can exceed 140 degrees Fahrenheit during sunny days, while nighttime cooling creates dramatic temperature swings that would challenge even the hardiest organisms. The chemical environment is equally harsh, with high concentrations of sulfur compounds and other volcanic gases creating conditions that would be toxic to most forms of life. Yet certain microorganisms, evolved over billions of years to survive in Earth's most extreme environments, find ways to thrive even here. Thermophilic bacteria, species adapted to high temperatures, establish the first biological communities in areas where geothermal activity keeps ground temperatures elevated. These pioneer organisms don't require organic nutrients. Instead, they derive energy directly from chemical reactions with the volcanic minerals around them, literally eating rock to fuel their life processes. These early microbial communities serve as the foundation for all subsequent biological colonization. As they live and die, they begin to create the first organic matter on the island, microscopic deposits of biological material that will eventually contribute to soil formation. More importantly, they begin to alter the chemical environment of the island's surface, creating microhabitats where slightly less extreme conditions allow other forms of life to establish themselves. The first macroscopic life to arrive on the island comes from the sea. Strands of marine algae, torn from their attachments by storms hundreds or thousands of miles away, wash up on the island's rocky shores. Most of these oceanic refugees perish quickly in the harsh terrestrial environment, but a few hardy species manage to survive in tide pools and other areas where seawater provides protection from the worst environmental extremes. These early marine colonists create the island's first visible ecosystems, small patches of green and brown that stand out dramatically against the black and grey volcanic landscape. These primitive seaweed communities don't just survive, they begin to modify their immediate environment in ways that make colonization easier for other organisms. As they photosynthesize, they add oxygen to local air and water. As they die and decompose, they contribute organic matter to the developing soil matrix. The arrival of the first terrestrial plants marks a crucial milestone in the island's biological development. These pioneer species, typically ferns, grasses, and other plants with lightweight spores that can travel long distances through the air, face the enormous challenge of establishing themselves on surfaces that contain virtually no soil or organic nutrients. The first successful plant colonists are invariably species adapted to extremely harsh conditions, plants that can tolerate high temperatures, intense solar radiation, and soils with unusual chemical compositions. Many of these early plant arrivals established themselves in the most unlikely places, in cracks in lava flows where wind-blown organic matter has accumulated, in areas where volcanic gases create slightly more moderate chemical conditions, or in the lee of larger rocks where they gain protection from the intense solar radiation reflected off dark volcanic surfaces. Each successful plant establishment creates what ecologists call a nurse site, a small area where conditions are slightly more moderate and where other organisms can potentially establish themselves. The process of plant establishment is slow and precarious. Seeds and spores may arrive on the island regularly, carried by wind or ocean currents, but the vast majority fail to find suitable conditions for germination and growth. Those that do establish themselves face constant challenges from drought, extreme temperatures, and the periodic burial by new lava flows that continue to reshape parts of the island's surface. But life, once it gains a foothold, demonstrates remarkable persistence and adaptability. The first successful plant communities begin to create their own favorable microclimates through processes that happen almost too slowly to observe. Their roots help break down volcanic rock through chemical weathering, gradually creating small pockets of more hospitable soil. Their bodies provide shade and wind protection, creating slightly cooler and more humid conditions that benefit other organisms. As they grow, live, and die, they contribute increasing amounts of organic matter to the developing soil. The arrival of animal life on the island follows patterns similar to those of plants, but with additional challenges related to the animals' need for food and suitable habitat. The first animal colonists are typically small, hardy species capable of surviving long journeys across open ocean and of subsisting on very limited food resources. Many early arrivals are marine species that use the island primarily as a resting or nesting site, while continuing to derive their nutrition from the surrounding ocean. Seabirds represent some of the most successful early animal colonists. Species adapted to long-distance ocean travel find that our island provides valuable resting sites during extended foraging trips. These early avian visitors don't immediately establish permanent colonies, but their presence begins to have important ecological effects. Their droppings, rich in nitrogen and phosphorus derived from marine food webs, provide the first significant inputs of nutrients to the island's developing terrestrial ecosystems. Some seabirds eventually transition from occasional visitors to permanent residents, establishing the island's first breeding bird colonies. These colonies, typically located on cliff faces or other areas relatively protected from volcanic activity, represent the establishment of the island's first stable animal populations. The birds not only add an important predator component to the developing ecosystem, but also serve as crucial vectors for dispersing seeds and other propagules around the island. Insects and other small arthropods represent another important group of early animal colonists. Many of these tiny creatures arrive by ballooning, allowing themselves to be carried by air currents across vast distances of open ocean. While the journey is perilous, and the vast majority of these aerial travelers perish before reaching suitable habitat, the few that successfully reach the island and find suitable conditions can establish populations that play crucial roles in pollination, decomposition, and other ecosystem processes. The early insect communities are typically dominated by species with broad dietary requirements and high tolerance for environmental extremes. These pioneer species often occupy ecological niches that are quite different from those they fill in their source populations. Adapting their behavior and ecology to take advantage of the unique opportunities and challenges presented by the island environment. As plant and animal communities become established, they begin to interact in ways that accelerate the pace of ecosystem development. Pollinating insects improve plant reproduction rates, while decomposer organisms help cycle nutrients through the developing soil systems. Predatory species help control herbivore populations, preventing overgrazing of the still vulnerable plant communities. The development of these ecological relationships creates positive feedback loops that make the island increasingly hospitable to new colonists. As soil depth and quality improve, a wider range of plant species can successfully establish themselves. As plant diversity increases, a greater variety of animal species find suitable food and habitat resources. Each successful colonization event makes future colonizations more likely to succeed. By the end of its first 100,000 years of existence, our island supports dozens of plant and animal species in communities that, while still simple compared to continental ecosystems, represent functioning ecological networks. Coastal areas support specialized plant communities adapted to salt, spray, and sandy soils. Interior areas, protected from the worst effects of wind and salt, begin to develop more complex plant communities that create increasingly shaded and humid microclimates. The island's first forests begin to emerge during this period, as tree species successfully establish themselves in areas where soil development and water retention have reached critical thresholds. These early forests are typically dominated by fast-growing pioneer species, but they create environmental conditions that will eventually allow the establishment of more diverse and complex forest communities. The transformation from sterile volcanic rock to living ecosystem represents one of the most remarkable processes in the natural world, the spontaneous generation of biological complexity from lifeless mineral substrates. Our island, once a simple pile of cooling lava, has become a center of biological diversity and evolutionary innovation, setting the stage for the continued development of unique ecosystems found nowhere else on Earth. To truly understand the magnificent process we've been witnessing, let's drift across the Pacific Ocean to observe one of Earth's most spectacular examples of volcanic island birth, the Hawaiian archipelago. Here, spread across 1,500 miles of ocean, we can see the entire life cycle of volcanic islands displayed like chapters in a vast geological storybook, each island representing a different stage in the process we've been following. The Hawaiian Islands sit above what scientists call the Hawaiian hotspot, a nearly stationary plume of superheated mantle material that has been creating islands for over 70 million years. But unlike our single island story, the Hawaiian chain tells a more complex tale, one of movement and renewal, where the ocean floor itself acts like a conveyor belt, carrying completed islands away from their birthplace while new ones are born to take their places. As we float above this island chain, we can see the story written clearly in the landscape below us. To the southeast lies the Big Island of Hawaii, the youngest and most volcanically active member of the chain. Here, we can witness volcanic island birth happening in real time, with active lava flows adding new acres to the island's surface every year. The island's southeastern shores glow with the red of molten lava meeting the sea, creating the same spectacular interactions between fire and water that marked our imaginary island's birth. Moving northwest along the chain, we encounter progressively older islands, each one representing a different chapter in the island formation story. Maui, with its massive Haleakala volcano, shows us what happens as volcanic activity begins to wane. The volcano still has the capacity for eruptions, but they occur infrequently, allowing other geological processes, erosion, weathering, and biological activity to begin reshaping the island's contours. Oahu presents us with an even more mature stage of island development. Here, the original shield volcanoes have been extinct for millions of years, but their massive bulk still dominates the landscape. Diamond Head and other iconic landmarks represent a later phase of volcanic activity, smaller eruptions that occurred long after the main shield-building phase ended. The island's landscapes show the profound effects of millions of years of erosion, creating the dramatic valleys and ridges that characterize mature volcanic islands. Kauai, the oldest of the main Hawaiian islands, shows us the ultimate fate of our volcanic creation. Here, nearly 6 million years of erosion have carved spectacular canyons and valleys into what were once gently sloping shield volcano surfaces. The island's Waimea Canyon, carved by millions of years of stream erosion, reveals the internal structure of the original volcano like a geological cross-section, showing us layers of ancient lava flows that tell the story of the island's fiery birth. But the Hawaiian chain doesn't end with Kauai. Extending northwest from the main islands, a string of increasingly small and eroded volcanic remnants traces the path of the Pacific Plate as it has moved over the Hawaiian hotspot. These older islands and seamounts, some now completely submerged, show us the ultimate fate of all volcanic islands: gradual subsidence and erosion until they disappear beneath the waves. The movement that creates this chain of islands results from plate tectonics, the slow but relentless motion of Earth's crustal plates. The Pacific Plate moves northwest at a rate of about 3 to 4 inches per year, carrying completed islands away from the hotspot while positioning new areas of seafloor over the rising mantle plume. This process has been creating and destroying islands in this region for tens of millions of years, with each island following the same basic pattern of birth, growth, maturity, and eventual disappearance. The Hawaiian chain also demonstrates how volcanic island formation affects entire ocean basins. The massive weight of these islands, each one representing billions of tons of volcanic rock, has depressed the underlying seafloor, creating what geologists call the Hawaiian swell. This broad depression in the ocean floor affects current patterns, sediment deposition, and marine ecosystems across millions of square miles of the Pacific Ocean. The biological story of the Hawaiian Islands provides equally compelling evidence of the island formation process. Each island's ecosystems reflect its geological age and history of volcanic activity. The Big Island, still actively growing through volcanic processes, supports ecosystems that range from active lava fields to some of the most diverse rainforests in the Pacific. But these ecosystems also show clear signs of their youth: relatively low species diversity compared to continental areas, and high levels of endemism as isolated populations adapt to unique island conditions. The older islands in the chain support more complex and mature ecosystems, with greater species diversity and more complex ecological relationships. But they also show the effects of human colonization more clearly, as their more developed soils and stable landscapes have made them more attractive for agriculture and urban development. The contrast between the raw volcanic landscapes of the Big Island and the heavily modified environments of Oahu illustrates how volcanic islands transition from geological to biological to cultural landscapes over time. The Hawaiian chain also provides crucial insights into how volcanic islands affect global climate and ocean systems. The islands create their own weather patterns, intercepting moisture-laden air masses and creating dramatic variations in precipitation across very short distances. The windward sides of the high volcanic mountains can receive over 400 inches of rainfall per year, while leeward areas may receive less than 20 inches. These precipitation patterns, in turn, affect everything from vegetation patterns to stream flow and groundwater recharge. The underwater portions of the Hawaiian Islands are equally remarkable. Each island's slopes extend far beneath the ocean surface, creating underwater habitats that support unique marine ecosystems. These submarine slopes, built by millions of years of lava flows extending from land into the sea, provide habitat for deep-sea corals, specialized fish communities, and other marine organisms found nowhere else on Earth. The Hawaiian Islands also demonstrate the importance of volcanic islands as stepping stones for biological dispersal across ocean basins. Species that successfully colonize one island in the chain can use it as a launching point for dispersal to other islands, creating patterns of biological diversity that reflect both geological history and evolutionary processes. Some species have colonized multiple islands in the chain, adapting to local conditions on each island and eventually evolving into distinct subspecies or species. Recent research on the Hawaiian Islands has also revealed the complex internal structure of these volcanic giants. Deep drilling projects have shown that the islands are built on foundations of pillow lavas, similar to those we observed during our imaginary island's submarine growth phase. Above these foundations, layer upon layer of subaerial lava flows record millions of years of volcanic activity, creating geological archives that preserve detailed records of past eruptions, climate changes, and even magnetic field reversals. The ongoing volcanic activity on the Big Island provides scientists with unparalleled opportunities to study volcanic island formation in real time. The current eruption of Kilauea volcano, which has been continuous for decades, has added hundreds of acres of new land to the island and provided detailed insights into how lava flows interact with ocean water, how new ecosystems establish themselves on fresh volcanic surfaces, and how volcanic gases affect local and regional atmospheric chemistry. Perhaps most remarkably, the Hawaiian chain shows us that volcanic island formation is not just a geological process, but a creative force that generates new opportunities for life and evolution. Each island becomes a natural laboratory where isolated populations of plants and animals adapt to unique conditions, often evolving into species found nowhere else on Earth. The chain as a whole represents one of the world's most important centers of endemism, with thousands of species that evolved in isolation on these remote volcanic peaks. As we contemplate the Hawaiian island chain from our peaceful vantage point above the Pacific, we can see that it represents something far more profound than just a collection of volcanic islands. It's a testament to the dynamic nature of our planet, a reminder that the Earth is constantly creating new land, new opportunities for life, and new wonders for us to discover and understand. While the grand story of volcanic island formation typically unfolds over hundreds of thousands of years, our modern world has been blessed with opportunities to witness the birth of new islands in real time. These contemporary examples of island formation provide us with unprecedented insights into the processes we've been exploring, allowing scientists to observe and document every stage of volcanic island birth with sophisticated instruments and techniques unavailable to previous generations. One of the most famous modern examples is Surtsey, an island that emerged off the coast of Iceland in 1963. For over 3 years, this underwater volcano battled against the North Atlantic's fierce waves and storms, gradually building itself above sea level through repeated explosive eruptions. The birth of Surtsey was witnessed by thousands of people and documented with unprecedented detail, providing the first complete scientific record of how a volcanic island emerges from the sea. The story of Surtsey began on November 14, 1963, when fishermen noticed steam and ash rising from the ocean surface about 20 miles off Iceland's southern coast. What they were witnessing was the moment when an underwater volcano, after perhaps months or years of submarine growth, finally approached close enough to the surface for its eruptions to break through the waves. The initial eruptions were violently explosive, as seawater rushing into the volcanic vent instantly vaporized upon contact with molten lava, creating towering columns of steam, ash, and volcanic fragments. For the first several months of its existence, Surtsey's survival was far from certain. The early island was composed mostly of loose volcanic debris called tephra, fragments of solidified lava that could be easily eroded by wave action. Storms repeatedly washed away portions of the growing island, and at times it seemed as though the ocean might reclaim what the volcano had built. But the volcanic activity was persistent and vigorous, and gradually the eruptions began to produce more substantial lava flows that created a solid foundation resistant to wave erosion. The transition from explosive submarine eruptions to effusive lava flows marked a crucial turning point in Surtsey's development. As the island grew larger and its central vent rose farther above sea level, the character of the volcanic activity changed fundamentally. The eruptions became less explosive and more sustained, allowing molten lava to flow across the island's surface and solidify into the dense, resistant rock needed to ensure the island's permanent survival. By the time volcanic activity on Surtsey ended in 1967, the island had grown to about 1.4 square miles in area and reached a height of nearly 600 feet above sea level. More importantly for our understanding of island formation processes, every stage of its birth had been witnessed, photographed, and scientifically documented. The detailed record of Surtsey's emergence provided crucial insights into the physical processes that govern how underwater volcanoes become permanent islands. But Surtsey's scientific importance extends far beyond its geological significance. Because the island was born in modern times under careful scientific observation, researchers were able to document the biological colonization process from the very beginning. Within months of the island's emergence, the first microscopic organisms, bacteria and primitive algae, were discovered on cooling lava surfaces. These findings confirmed theories about how life first arrives on new volcanic islands and provided detailed documentation of the earliest stages of ecosystem development. The biological colonization of Surtsey has been studied continuously for over half a century, providing an unparalleled record of how life establishes itself on newly formed land. The first plants appeared within a few years of the island's formation, with mosses and grasses taking hold in areas where wind-blown organic matter had accumulated. Seabirds began using the island as a resting site almost immediately, and their droppings provided crucial nutrients that helped establish more complex plant communities. Today, Surtsey supports dozens of plant species and serves as a nesting site for several seabird species. The island has been designated as a UNESCO World Heritage Site, recognized not only for its geological significance, but also for its value as a natural laboratory where scientists can study ecological succession and evolution in action. Access to the island is strictly controlled to prevent human interference with ongoing natural processes. In the Pacific Ocean, we have witnessed even more recent examples of volcanic island birth. The island of Nishinoshima, near Japan, dramatically renewed its growth in 2013 after decades of dormancy, expanding from a tiny outcrop to a substantial landmass through continuous volcanic activity. This modern eruption provided scientists with opportunities to use satellite imagery, underwater cameras, and other advanced technologies to document island formation with unprecedented detail. The Nishinoshima eruption began with underwater explosive activity similar to what we observed in Surtsey's birth. However, the availability of real-time satellite monitoring allowed scientists to track the volcano's progress from its first submarine eruptions through its eventual emergence above sea level. Time-lapse satellite images created a stunning visual record of how the new land gradually expanded, showing the island growing from a few acres to over 1,000 acres within just a few years. One of the most remarkable aspects of the Nishinoshima eruption was how it demonstrated the speed with which modern volcanic islands can grow once they establish themselves above sea level. The island's land area increased by over 2,000% during the most active phase of the eruption, showing that under favorable conditions, volcanic island formation can proceed remarkably rapidly. The eruption also provided detailed data on how volcanic islands affect local ocean conditions, marine ecosystems, and atmospheric chemistry. The ongoing volcanic activity in the Galapagos Islands provides another modern window into island formation processes. The western islands of the archipelago, particularly Fernandina and Western Isabella, remain highly active volcanically and continue to grow through ongoing eruptions. These islands allow scientists to study not just the birth of new land, but also how continued volcanic activity shapes island ecosystems over longer time periods. Recent eruptions in the Galapagos have been particularly valuable for understanding how volcanic activity affects established ecosystems. Unlike newly formed islands where life must colonize sterile volcanic surfaces, the Galapagos eruptions occur on islands that already support complex biological communities. Scientists have been able to document how these communities respond to volcanic disturbance, how quickly they recover, and how new lava flows are colonized by plants and animals from surrounding areas. The advent of underwater robotics and deep-sea exploration technology has also allowed scientists to study the submarine stages of island formation with unprecedented detail. Underwater volcanoes that may eventually become islands have been discovered and monitored throughout the world's oceans. These submarine volcanoes, in various stages of development, provide insights into the early phases of island formation that were previously impossible to study directly. One particularly well-studied example is Loihi Seamount, located southeast of the Big Island of Hawaii. This underwater volcano is actively growing and is expected to emerge above sea level within the next 10,000 to 100,000 years, making it the Hawaiian chain's next island. Scientists have established permanent monitoring stations on Loihi, providing continuous data on submarine volcanic activity, hydrothermal systems, and the development of unique deep-sea ecosystems around active underwater volcanoes. The study of Loihi has revealed that submarine volcanic activity creates complex hydrothermal systems that support unique forms of life adapted to high temperatures and unusual chemical conditions. These hydrothermal communities may represent modern analogues for the earliest forms of life on Earth, making underwater volcanic systems important not just for understanding island formation, but also for studying the origins and evolution of life itself. Modern monitoring technology has also revealed that many underwater volcanoes experience cycles of growth and collapse that were previously unknown. Some seamounts grow for thousands of years, building substantial underwater mountains, only to collapse catastrophically when their internal structure becomes unstable. These collapse events can destroy decades or centuries of volcanic construction in a matter of hours, illustrating the dynamic and sometimes violent nature of underwater volcanic systems. Recent research has also shown that climate and sea level changes can significantly affect volcanic island formation. During ice ages, when sea levels were hundreds of feet lower than today, many underwater volcanoes that are currently submarine were able to emerge above sea level and build substantial sub-aerial portions. When sea levels rose again as ice sheets melted, these temporary islands were submerged, but their remains can still be detected using modern seafloor mapping techniques. The study of modern volcanic island formation has also revealed the important role these systems play in global ocean circulation and climate regulation. Active underwater volcanoes release enormous quantities of heat, dissolved minerals, and gases into the ocean, affecting water chemistry and circulation patterns across entire ocean basins. The biological communities that develop around these systems also play important roles in oceanic carbon cycling and nutrient distribution. Perhaps most remarkably, modern observations have shown that volcanic island formation is far more common than previously thought. Advanced seafloor mapping has revealed thousands of underwater volcanoes in various stages of development throughout the world's oceans. While only a small fraction of these will eventually become islands, their existence demonstrates that the process of island formation is ongoing and widespread, making it one of the most important geological processes shaping our planet's surface. As we consider these modern examples of island birth, we're reminded that the process we've been following is not just a historical curiosity, but an active, ongoing force that continues to shape our planet. Each new island that emerges from the sea represents a unique opportunity to study fundamental geological and biological processes, providing insights that help us understand not just how islands form, but how life itself adapts, evolves, and thrives in Earth's most extreme and dynamic environments. As we approach the end of our journey through the life of volcanic islands, it's time to contemplate one of the most profound aspects of this geological story: the recognition that island birth is just one part of an eternal cycle of creation and destruction that has been shaping our planet for billions of years. The islands we've watched emerge from the sea in fire and steam are not permanent fixtures on Earth's surface, but temporary creations that will eventually return to the ocean depths from which they arose. This cycle of death and rebirth operates on timescales that dwarf human experience, yet its effects are visible everywhere we look in the world's oceans. The Hawaiian island chain, which we explored as an example of volcanic island formation, also provides us with a clear illustration of island death. As we travel northwest from the currently active volcanoes of the Big Island, we encounter islands in progressively more advanced stages of decay and erosion. The process of island aging and eventual disappearance begins almost as soon as volcanic activity creates new land above sea level. Even during the height of shield building, when volcanic eruptions are constantly adding new material to an island's bulk, the forces of erosion are simultaneously working to tear down what the volcano builds. Rain falls on fresh volcanic surfaces, beginning the chemical weathering process that gradually breaks down solid rock into sediment. Waves crash against coastal cliffs, undermining their foundations and causing periodic collapses that carry tons of volcanic rock back to the sea. But for young, volcanically active islands, the rate of construction typically exceeds the rate of destruction. As long as eruptions continue to add new material faster than erosion can remove it, the island continues to grow. However, this balance inevitably shifts as the island moves away from its source hotspot, or as the underlying mantle plume weakens. When volcanic activity declines and eventually ceases, erosion gains the upper hand in this ancient battle between construction and destruction. The transition from active volcanic island to eroding remnant happens gradually, over millions of years. As major eruptions become less frequent, the island's profile begins to change subtly. The gentle, shield-like slopes created by fluid lava flows become increasingly dissected by stream valleys as rainfall carves channels into the volcanic rock. These valleys, initially small and shallow, gradually deepen and widen as countless centuries of flowing water carries away countless tons of eroded material. On older islands, this erosion process creates some of the most spectacular landscapes on Earth. The dramatic knife-edge ridges and deep valleys of islands like Kauai in the Hawaiian chain or the older Canary Islands represent millions of years of water sculpting solid volcanic rock. These eroded landscapes reveal the internal structure of the original shield volcanoes, exposing cross-sections of ancient lava flows and providing insights into the volcanic processes that built the islands millions of years ago. The erosion process is not uniform across an island's surface. Differences in rainfall, rock type, and structural geology create dramatic variations in erosion rates. Windward slopes, which receive more rainfall, typically erode much faster than leeward areas. Valleys carved along zones of weakness in the volcanic rock can become spectacularly deep canyons, while more resistant rock formations remain as towering ridges and peaks. As islands age and erode, their biological communities also undergo profound changes. The dramatic topographic relief created by erosion generates diverse microclimates that can support much greater biological diversity than the relatively uniform environments found on young volcanic islands. Deep valleys may preserve remnants of ancient ecosystems, while isolated ridges become island-like habitats where endemic species evolve in isolation. However, The same erosion processes that create diverse habitats also threaten island ecosystems by reducing the total land area available for terrestrial life. As stream valleys deepen and coastal cliffs retreat inland, the overall size of islands gradually decreases. Some plant and animal populations may be eliminated as their preferred habitats disappear, while others may be forced to adapt to changing conditions or face local extinction. The ultimate fate of volcanic islands is determined not just by surface erosion, but also by large-scale geological processes operating deep beneath the Earth's surface. As islands move away from the hotspots that created them, the underlying oceanic crust gradually cools and contracts, causing the islands to subside slowly back toward sea level. This subsidence, combined with ongoing sea level changes related to global climate cycles, means that even islands that successfully resist surface erosion may eventually be claimed by the rising sea. The northwestern Hawaiian Islands provide a clear example of this subsidence process. These islands, once as large and mountainous as the current main Hawaiian Islands, have been gradually sinking back toward sea level as they've moved away from the Hawaiian hotspot. Many are now little more than low coral atolls or completely submerged seamounts, their volcanic origins evident only to geologists who study their underwater remains. But the story doesn't end with island disappearance. The same mantle plumes and hotspots that created the vanished islands continue to operate, building new islands to replace those that have been claimed by time and the sea. This is the eternal cycle that gives our story its deeper meaning, the recognition that destruction and creation are not opposite forces, but complementary aspects of the same fundamental process. The materials that erosion carries away from dying islands don't simply vanish into the ocean depths. Instead, they become part of vast sedimentary systems that redistribute volcanic material across entire ocean basins. The black sand eroded from Hawaiian beaches may eventually be deposited on the seafloor thousands of miles away, while the dissolved minerals released by chemical weathering of volcanic rock contribute to the chemical composition of seawater worldwide. Some of this eroded material may even find its way back into the volcanic systems that originally created it. As oceanic plates move and subduct beneath continental margins, sediments derived from ancient volcanic islands are carried deep into the Earth's interior, where they may eventually be incorporated into new magma and erupted again in distant volcanic systems. In this way, the atoms that once formed towering volcanic peaks may be recycled through the Earth's interior and eventually contribute to the formation of new islands in entirely different parts of the world's oceans. The biological legacy of vanished islands also persists in unexpected ways. Many of the unique species that evolved on now submerged islands managed to disperse to younger islands before their original homes disappeared beneath the waves. These biological refugees carry with them genetic information and evolutionary adaptations forged on ancient volcanic landscapes, contributing to the biological diversity of newer islands and ensuring that something of the vanished island's living heritage survives. Modern molecular genetics has revealed that many island species carry DNA signatures that tell stories of multiple colonization events and inter-island dispersal spanning millions of years. Some lineages have survived the disappearance of multiple ancestral islands, adapting repeatedly to new volcanic landscapes as they dispersed across island chains. These genetic time travelers provide living links between vanished worlds and contemporary ecosystems. The cycle of island birth, growth, maturity, and death also plays crucial roles in global ocean circulation and climate regulation. Young, tall volcanic islands create obstacles to atmospheric circulation that affect weather patterns across entire ocean basins. As these islands age and erode, becoming lower and eventually disappearing, they alter the paths of air and water currents in ways that can influence climate conditions thousands of miles away. The submarine portions of the island cycle are equally important to global ocean systems. As islands subside and become seamounts, they continue to affect deep ocean currents and serve as stepping stones for the dispersal of deep-sea organisms. The complex topography created by chains of seamounts, the submerged remains of ancient islands, creates upwelling systems that bring deep, nutrient-rich water to the surface, supporting some of the world's most productive marine ecosystems. Recent scientific research has revealed that the island formation cycle operates on multiple timescales simultaneously. While individual islands may exist for millions of years, the hotspots that create them operate for tens of millions of years, and the mantle convection systems that drive hotspot activity may persist for hundreds of millions of years. This nested hierarchy of temporal scales means that island formation is not just a local geological process, but part of the fundamental dynamics that drive plate tectonics and shape the Earth's surface on a global scale. The recognition of this eternal cycle also helps us understand the deep history of life on Earth. Many of the world's most isolated ecosystems exist on volcanic islands that represent temporary way stations in the endless process of island creation and destruction. The unique evolutionary pressures created by island environments have contributed to some of the most remarkable adaptive radiations in the biological world, generating new species and even new body plans that might never have evolved in continental environments. As we contemplate the eternal cycle of volcanic island formation, we're reminded that our own planet is not a static, unchanging world, but a dynamic system in constant flux. The solid ground beneath our feet, which seems so permanent from our human perspective, is actually engaged in continuous processes of creation, transformation, and renewal that operate on scales far grander than individual human experience. The volcanic islands we've followed through their life cycles represent just one manifestation of these deeper planetary processes. Every mountain range, every ocean basin, every continent bears the marks of similar cycles of creation and destruction operating on even grander scales. The Himalayas are rising even as they're being eroded away. The Atlantic Ocean grows wider by inches each year as new seafloor is created at mid-ocean ridges. Ancient continents fragment and disperse, while new continents form from the collision of tectonic plates. Understanding the island formation cycle also provides perspective on humanity's relationship with our changing planet. The timescales involved in island formation and destruction dwarf not just individual human lifespans, but the entire history of human civilization. Yet these processes continue to shape the world we inhabit, creating new land, new opportunities for life, and new challenges for the species that call volcanic islands home. Perhaps most profoundly, the story of volcanic island formation reminds us that creation and destruction are not opposing forces, but complementary aspects of the same fundamental process of planetary renewal. The fire that destroys also creates. The waves that erode also redistribute. The movements that tear apart also bring together. In recognizing this eternal cycle, we gain a deeper appreciation for the dynamic, ever-changing nature of our remarkable planet and our place within its continuing story of transformation and renewal. As we conclude our journey through the life cycle of volcanic islands, we carry with us an understanding that extends far beyond geology or biology. We've witnessed one of the most fundamental processes by which our planet renews and recreates itself, ensuring that even as old worlds disappear, new worlds are always being born. In the endless cycle of volcanic island formation, we see reflected the deeper rhythms that govern all existence. The recognition that endings are also beginnings, that destruction enables creation, and that change itself is the only constant in our ever-evolving world. As our long journey through the life of volcanic islands draws to a close, let's take a moment to float peacefully above the vast Pacific Ocean, watching the sun set over waters that stretch endlessly toward the horizon. The surface is calm now, painted in shades of gold and amber by the setting sun, giving no hint of the magnificent creative forces that work tirelessly in the darkness thousands of feet below. Tonight, we've traveled together through one of Earth's most patient and persistent acts of creation. We've watched as tiny cracks in the ocean floor became underwater mountains, as submarine volcanoes battled against the sea itself to create new land, and as bare volcanic rock transformed into living ecosystems that support some of the world's most unique and beautiful forms of life. We've seen how the Earth builds islands grain by grain, eruption by eruption, across spans of time so vast they challenge our human understanding of permanence and change. In following this story, we've witnessed something far more profound than just a geological process. We've observed the Earth itself as a living, creating, constantly changing system that never rests in its work of renewal and transformation. The volcanic islands we've watched emerge from the sea represent just one of countless ways our planet continues to reshape itself, creating new opportunities for life and new wonders for future generations to discover. Think of the patience involved in this process, the thousands of years of submarine growth before the first tentative emergence above the waves, the centuries of explosive eruptions battling against ocean storms, the millennia of steady lava flows building broad foundations for future ecosystems. This is patience on a scale that dwarfs human experience, yet it's motivated by the same creative force that drives all life and growth in our world. We've also seen how profoundly interconnected all of Earth's systems truly are. The molten rock that builds islands begins its journey in the planet's deep interior, carrying with it chemical signatures from depths we'll never directly explore. The life that colonizes new islands travels across thousands of miles of open ocean, connecting distant ecosystems in webs of relationship that span entire ocean basins. The weather patterns created by volcanic mountains influence climate conditions thousands of miles away, while the islands themselves eventually contribute their eroded remains to sedimentary systems that span the globe. In the story of volcanic islands, we find a beautiful metaphor for many of the processes that shape our own lives. Like these islands, we often face periods of explosive change, followed by long intervals of steady growth. We build our own foundations through patient accumulation of experiences, knowledge, and relationships. We weather storms that threaten to wash away what we've built, yet we persist and continue growing. And like islands, we exist within larger systems of relationship and connection that extend far beyond our individual boundaries. The biological colonization of volcanic islands also offers profound lessons about resilience, adaptation, and the power of life to thrive in even the most challenging environments. The first microscopic organisms that established themselves on cooling lava, the pioneer plants that found footholds in seemingly impossible conditions, the animals that traveled vast distances across empty ocean to reach new shores, all represent the same spirit of exploration and adaptation that characterizes life at its most creative and resilient. We've learned that creation and destruction are not opposing forces, but complementary aspects of the same fundamental process of renewal. The volcanic eruptions that destroy existing landscapes also create the foundations for new ones. The erosion that gradually wears away ancient islands also provides the raw materials for new soil and new habitats. The movements of tectonic plates that carry islands away from their birthplaces also position new areas of seafloor over the hotspots that will create future islands. This eternal cycle of renewal offers us comfort and perspective as we face the changes and challenges in our own lives. Nothing in this world is truly permanent. Not the mightiest mountains, not the deepest oceans, not even the continents themselves. Yet this impermanence is not a cause for despair, but a source of hope, because it means that endings are also beginnings, that what seems like destruction often enables new forms of creation, and that our dynamic, ever-changing world is always generating new possibilities and new opportunities for growth. The timescales involved in volcanic island formation also offer us a different perspective on time itself. In our fast-paced world, where change is often measured in minutes or seconds, the story of islands reminds us of the value of patience, persistence, and long-term thinking. The most magnificent creations, whether they're volcanic islands, great ecosystems, or human achievements, often require sustained effort over extended periods. They grow not through dramatic leaps, but through countless small contributions, each one building upon what came before. As we've seen in the examples of modern island formation, we live in a remarkable time when advanced technology allows us to witness these ancient processes in real time. The emergence of Surtsey, the growth of Nishinoshima, the ongoing monitoring of underwater volcanoes, all represent unprecedented opportunities to observe and understand the forces that have been shaping our planet for billions of years. These modern observations remind us that the Earth's creative work is not something that happened only in the distant past, but continues all around us, often in places and ways we're only beginning to understand. The story of volcanic islands also reminds us of our responsibility as stewards of these remarkable places. Many of the world's most beautiful and biologically diverse volcanic islands face increasing pressure from human activities. Climate change, development, invasive species, and pollution all threaten the delicate ecosystems that have evolved over millions of years on these remote volcanic peaks. Understanding how these islands formed and how their ecosystems developed gives us greater appreciation for their value and urgency to protect them for future generations. As we prepare to let sleep carry us away into our own peaceful depths, we can take with us the profound sense of wonder and perspective that comes from understanding our place within the larger story of our dynamic planet. We are temporary inhabitants of a world that is constantly recreating itself, constantly generating new forms of beauty and complexity, constantly reminding us that change and growth are the fundamental characteristics of existence itself. Tonight, as you drift off to sleep, you might imagine yourself floating peacefully above the vast ocean depths, knowing that even now, in the darkness far below, the earth continues its patient work of creation. Somewhere beneath the waves, molten rock is slowly rising through layers of solid stone. Somewhere else, a crack is appearing in the ocean floor that will become the birthplace of a future island. And somewhere in the depths, life is finding ways to thrive in conditions that seem impossible, preparing for the eventual colonization of lands that do not yet exist, but will someday rise from the sea in clouds of steam and sprays of molten rock. Rest well, knowing that you are part of this magnificent, ever-creating world, a world that never stops building, never stops growing, never stops finding new ways to surprise and inspire us with its boundless creativity and endless capacity for renewal. The same forces that build islands from the seafloor also shape our daily lives, reminding us that we too are part of the Earth's continuing story of growth, change, and creative transformation. In the gentle rhythm of your breathing, you can hear an echo of the patient persistence that builds mountains from the sea. In the warmth of your body, you can feel a connection to the same energy that powers volcanic eruptions and creates new land. And in the peace of approaching sleep, you can find the same calm that exists in the deep ocean depths where tomorrow's islands are even now beginning their long, slow journey toward the light. Sweet dreams, fellow travelers on this remarkable planet. May your rest be as deep as the ocean basins, and your dreams as creative as the forces that build islands from fire and stone. Good night!